Hello. Welcome back to Chapter 14 of Calculus 3. We're just starting that today. Chapter 14 is multiple integration. Need a better pen. Yeah, double integrals, triple integrals. Okay, this is going to be awesome. So, let's try one. I'm going to do a double integral. I'm going to integrate a function of x's and y's. Let's see here. 3x squared y minus 2 cosine 3x plus y e to the x dy dx. So I'm integrating this function. It's a crazy function of x's and y's. A function of x's and y's. I'm integrating it with respect to dy first and then dx. The bounds for the inner integral dy is, I'm going to make these bounds 0 to x, and then the bounds for x, I'll just make it 0 to 1. So I just made up this problem. This is a typical double integral, and I kind of want to, I'll tell you what it means a little later. Right now, I just kind of want you to do it. The book, it's called a double integral. The book also calls this an iterated integral. Because you do it in iterations. You do one integral and then you do the next integral, and you work your way inside out. So you start by working with the inner integral, which is kind of this integral, and this inner integral is with respect to y. So you are integrating with respect to the variable y. So you treat all the other variables like they're constants. So we integrate with respect to y, treat the x like it's a constant. So it's been a while since we integrated. Let's try integrating with respect to y. I think I would do a power rule, y squared over 2. The 3x squared is a constant, so 3 halves x squared y squared. That's y squared divided by 2. That's how you integrate. Let's see, how do you integrate this with respect to y? With respect to y, oh, it's just a big constant. And how do you integrate a big constant? I think it's this times y. Yeah, this times y. Okay. What am I doing now? Integrating this with respect to y. Okay, well, the e to the x is a constant, so I'm integrating this y with respect this y, e to the x. The e to the x is a constant, so I'm integrating the y like a y squared over 2 multiplied by the constant. Yeah, that's awesome. I just integrated with respect to y. I'm going to evaluate with my bounds 0 to x. Those are the bounds for this inner integral. And then what happens is you're plugging these bounds in for the variable y. So here we go. When I plug this x in for y, I get 3 halves x to the 4th. When I plug this x in here, I'm going to move it out front. It's a negative 2x cosine of 3x. When you plug this x in here, it's x squared over 2, e to the x. Minus, you're supposed to plug the 0 in for all those y's, but when you plug a 0 in for that y, and 0 in for that y, and a 0 in for that y, you get a bunch of zeros here. So, subtracting a bunch of zeros. So the answer to the inner integral is this. And notice, all the y's are gone. Now it's just a function of x. And what am I supposed to do with it? Now I'm supposed to integrate it with respect to x. So now I'm integrating this function from 0 to 1 with respect to x. Those are a bunch of zeros down there. Well, good luck. There's some challenges in here, actually. That's okay. We can handle some challenges. First off, it's not much of a challenge. To integrate 3 halves x to the 4th, you power rule, x to the 5th, divide by 5. 3/10 x to the 5th, I believe. But to integrate this, you know, with integration we don't have product rules. What we have is integration by parts. I'm afraid I'm going to need it there also. Integration by parts. I didn't really plan on 2 of them, but that's okay. I want to do integration by parts. There's a shortcut for integration by parts. It's called the Tabular Method. That's what I want to do. I'm going to go over here to my scrap paper. I'm going to remind you how to do integration by parts. You know, by the way, the integration by parts formula back from Chapter 8 in Cal 2 was the integral of a u dv is uv minus the integral of a v du. So that's integration by parts. But for certain situations, there's a shortcut tabular method for this. I can set up a table where I identify u and I identify dv. I'm going to call u, for this integral right here, I'm going to call u the 2x. And I'm going to call the dv the cosine of 3x. Alright, so now what? Now you differentiate the u to get du. That's a 2. You do it again and it goes away to 0. You take derivatives of u. You actually do little mini integrals here. You integrate dv to get v. Integrate cosine 3x. I think you get sine 3x. The derivative of sine is cosine. The integral of cosine is sine. Yeah, it's a sine 3x. Technically, there's a little u substitution that spits out a 1/3. We just integrated right there. Let's integrate again. I guess we get negative 1/9 cosine 3x. Integrated. We should put a plus and a minus and a plus here, and the answer to this integration by parts of this term right here, I'm integrating this term right here with integration by parts, the answer is this and this added together. So I'm going to write that. That's a 2/3, that's a multiplied term there. It's positive 2/3 x sine 3x. It's positive 2/3 x sine 3x. You know, one thing I did when I worked on this problem, there's a negative sign in front of it, and I guess I sort of kept the negative sign out in front. So this answer was positive, there is this negative sign in front. Here comes more of the answer though. Here comes a positive, that's a positive 2/9 cosine 3x. It's positive, but this negative sign in front is going to make it negative 2/9 cosine 3x. Wow. That was integrating by parts. Using the shortcut tabular method saved me a little time. Guess what? I got to integrate this by parts. This one's a little easier. Let's do it. Off to my scrap paper. I'm integrating x squared over 2 e to the x using the tabular method. Is that what it was? X squared over 2 e to the x. Here we go. The u and the dv. I would identify the u as the x squared over 2, and I would take a derivative. Bring the 2 down, 2x over 2, that would just be an x. Take another derivative, you get a 1. Take another derivative, you get a 0. I think I did that right. Over here we put a plus, minus, a plus, a minus. And over here we identify the dv as e to the x, and we integrate. Integrating e to the x is the funnest thing in the world. That's what they say. Here we go. The answer to this integration by parts is this term, plus this term, or minus, and plus this term. The answer is an x squared over 2 e to the x, minus an x e to the x, plus an e to the x. Wow, you guys. That's that integral. Had a couple integrations by parts all in this same integral. Sorry about that, but it made it a nice long integral. Now it needs to be evaluated from 0 to 1. You know, plug in a 1, plug in a 0, see what happens. It might be fun, it might be interesting. Let's try this. If I plug in a 1, I'm going to get a 3/10. If I plug in a 1, this is a little weird, but it's negative 2/3 times the sine of 3. Of course, that's some number. That's the sine of 3 radians. That's what that is. This is minus 2/9 the cosine of 3 radians. Whatever that is. Plugging in a 1 here, this is 1/2 e to the first. Plus 1/2 e to the first. Minus 1 e to the first. That's interesting. And then finally, just a plus e to the first. Okay, all right, that's what happens when you plug in a 1. Minus, what happens when we plug in a 0? When we plug in a 0, that's a 0, that's a 0. Turns out, though, the cosine of 0 is a 1. So I get a negative 2/9. And that's a 0, that's a 0, but it turns out e to the 0 is a 1. So I get a 1 right there. Woohoo, what a mess. That's the answer to this crazy double integral I made up. Somebody should have stopped me. Multiple integration. We made up a hell of a double integral. It definitely involves some integration by parts on the second go-round there. The first integral was with respect to y. It was kind of easy. Then with respect to x, I had some work to do. Again, there's my answer. I'll keep cleaning because I like it nice and clean. What do I have here? I've got this 3/10 minus this 2/3 sine of 3. I'm not doing much with that. Minus 2/9 cosine of 3. I'm not doing much with that. You know, I think these e's right here cancel. But I do have this 1/2 an e, I guess, plus 1/2 an e. And, you know, this is a 7/9 if you add that together. But it's minus 7/9. Yeah, you know, I'm going to circle that and call that my answer. If I was going to combine a couple like terms, I guess I'd add the 3/10 and the negative 7/9. It might be fun to pick up a calculator and tell me what this number is. It is just a number. Better be in radian mode. It looks like a negative number, maybe. Who knows? It looks like it could be negative. I'm going to try it. I'm going to try it. Well, I hit enter after all that, and I've got a nice little teeny positive number here. I'm getting a 1.00728, blah, blah, blah. Huh, that's interesting. It's practically a 1. That's interesting. When my little grandbaby turns 1 year old, you know, she won't care about this rounding off. Maybe I'll just put this, I'll say happy 1 year birthday, but what I'll do is I'll put this on her cake. Basically, we did this double integral and it came out to approximately 1. Yeah, that's just a 1. What is that 1, or 1.007? What is this? What are we doing? So anyway, what I just tried to teach you was how to do a double integral. So hopefully you caught that. What does it mean? Well, let's try this. Let's try this. What we just did was this. A double integral of some function of x's and y's over a region R. We integrated this function, and by the way, this is z. You know that this is z. So this is some 3D surface. We integrated this 3D surface over the region R, and we integrated with respect to A, the area of that region R. Now, my little dA turned out to be, in this problem, turned out to be dy dx. There's other problems where it's dx dy. Let me try to illustrate this. Sort of abstractly here, if you don't mind. I'm not going to specifically draw this function. But abstractly, what we have is a 3D surface of some sort living up above the xy plane, and that's not necessarily true. It could be below the xy plane or partially above and partially below, but for purposes of this illustration, we're integrating some surface, z equals f of xy, over, and we're integrating this over some region in the xy plane. We're integrating over some region in the xy plane. So maybe we're not integrating the whole entire surface. Maybe we're just integrating over this region. You know? We're just integrating the part of the surface that lives over this region. Though that region was well described with the bounds of the integral. Those bounds describe a region. So we're integrating a 3D surface over with respect to the area of the region R in the xy plane. What we're finding when we do all this is the volume of that thing, whatever that thing is. We're finding the volume of this. This is, I'll tell you what this is. This is the volume between the surface, f of x, I'll say z equals f of xy, and the region R in the xy plane, described in the bounds. Yeah, maybe I'll just say that. The volume between the surface and the region in the xy plane. It's like we're slicing this little region up into little cross sections, and I'll blow this up a little bit. This little change in x is dx. This little change in y is dy. Together, when you multiply dx dy, it's a lot like multiplying length and width of this little rectangle. And that's the dA, that's the dA of that little chunk of area. So we're slicing this region up into all kinds of little chunks of area. We're calculating the height for over that little area. We're multiplying height times area. We're getting volume. We're multiplying height times the little area of the base. We're getting volume. We're adding that all up, doubly adding it up as we move in the x direction and then cross over in the y direction. Or I did that backwards, x and y direction. Yeah, that's what a double integral is, loosely, or as best I can do. So you know what? Let's go back and look at our specific one. So our specific surface is a damn mess. I'm not going to be able to draw that for you. But what I definitely can draw for you, and there's full of exercises in 14.1, is I can draw the region over which I'm integrating. The region over which I'm integrating is in the xy plane. It's this region R, and it's totally described here in these bounds. And it really is sort of separate from the function itself. The function itself lives up there. The region is described with these bounds. And they're kind of two unrelated things, except they're related in the sense of doing this integral. So what region am I integrating over? I'm integrating some crazy function, but I'll tell you what, in the xy plane, look, I'm just going to draw the xy plane. What do I have here? This says, now who was this inner variable? Who was this inner variable? This was y. It says that y goes from 0 to x. So y goes from 0 to y equals x. Another way to state that is the variable y lives between x and 0. Well, first of all, let's draw y equals 0. Y equals 0 is this. Okay, sorry. Let's draw y equals x. Okay, y equals x is this. All right, so the bound y goes from 0 to x. The bound y goes from y equals 0 to y equals x. That's awesome. And it does that forever? No, it doesn't do that forever. Let's look at the bounds out here. These bounds, and by the way, these bounds are for x. These outer bounds are for x, and it says to me that x is living between 0 and 1. So while y moves from 0 to x moves from 0 to 1, and this is the region over which I'm integrating. Y goes from 0 to x goes from 0 to 1. This is a little triangular region. I'm integrating whatever the surface is doing. The 3D surface lives up here over this region. I'm integrating the 3D surface over this region. It comes up, it's got this bumpy surface on top. I guess the volume of this damn thing, whatever it is this, approximately 1. You know, this double integral, if this surface slices below the xy plane, I like to draw it above the xy plane, but if the surface slices below the xy plane, the volume between the surface and between the xy plane and the surface below it, the integral is going to call that volume negative. When the surface is above the xy plane, the volume between the surface and the region where it's above in the xy plane, it's going to call that positive. You know, what I got out of this crazy problem was a positive answer. But that doesn't mean the whole entire surface was above. It just means the kind of, maybe I should call this the net volume. I called it the volume between the surface. Maybe I should call it the net volume. Because maybe some of this surface was below the xy plane and some of this volume was negative, some of this volume was positive. In the end, positive 1 by an amount of roughly 1. If that makes any sense. It does. There's a surface above here, and the volume between this surface and this is 1. But it may not be totally above. Maybe some of it is slicing through. So maybe there's some negative volume, some positive volume. The net volume, though, is 1. Interesting. It's just a hell of a surface. I'm not sure what's going on. It might be slicing through there. Yeah, that's cool, you guys. And that's great notes. Now here's the funny little thing. I don't want to confuse you here. We could do a simpler problem. But your book starts off in 14.1. And they got some problems kind of like this. They just want you to crank out some problems. They don't worry about what it means too much. I kind of jumped up. When I told you what this meant, I really sort of jumped up into 14.2 here. What they say in 14.1 when you start this section is they say you're working on these double integrals, and for a while there they don't even put a function in there. They just say it's a 1. You know, there's no z, there's no function there in a way, unless you call it 1. Z equals 1. So then you're just integrating with respect to the area of the region R, and then they don't call this volume, even though a double integral is volume. They call this the area of the region R. I'll tell you what, let's play this game a second. Let's play this game a second. Back in Cal 1, if I said, hey, here's a function f of x, here's a function g of x, I want the volume, area, between this number A and this number B. I want this area. Back in Cal 1, we can do this area, or maybe this was a Cal 2 question. Anyway, it's just area. And area is, when you have two functions like that, we would call it the area between the curves. And if you want the area between the curves, I recall teaching you that that's the top curve minus the bottom curve with respect to x. So you set up an integral from A to B, from A to B, top curve minus bottom curve gives you the area between the two curves. So you integrate f of x minus g of x with respect to x. Okay, cool. And that's area. And that's Cal 1 and it's area. It's a single integral and we all know that. If you do this problem today in chapter 14, you would set up a double integral. You would go like this. You would set up a double integral. You wouldn't integrate anything here. You'd put a 1 right here. You'd integrate dA. But now your dA is, like I said a few minutes ago, the dA is either dy dx or dx dy, your choice of order of integration. I'm going to choose dy dx. So here's my dA, dy dx. That means I'm integrating y first. So I'm going to go look at this picture. I'm going to, instead of generically integrating over a region R, my region R is defined here in this picture. This is my region R. And instead of just generically saying I'm integrating over a region R, I'm going to fill in the bounds here. Watch. It is sort of generic, but here we go. I'm going to fill in the bounds. If y is varying, then I let y vary first. And I kind of just put an arbitrary y stick in there. You know, it could be here, it could be here, it could be anywhere. But wherever you put it, I think there's clearly a bottom y called g of x and a top y called f of x. And I think you would tell me that the bounds for y should go from the bottom to the top. The bounds for y are g of x to f of x. And while y is doing that, going from g of x to f of x, then I think x should go to the extreme left and the extreme right. I think x should go from A to B. And that's area using a double integral in Cal 3. We already knew how to do area in Cal 1, but this is area using a double integral. And let me just prove to you they're the same thing. Watch. Please integrate this with respect to y. It's a number 1. If you integrate with respect to y, you get y. And then you have to evaluate with your bounds from g of x to f of x. So you're plugging in an f of x for your variable y, and you'll get f of x. Minus, you plug in your g of x, you'll get g of x. And then you're left with you've finished the inner integral, and you're left with the outer integral from A to B. Please integrate with respect to x. And that's the same thing we had a second ago. That's Cal 1. So in one step, this double integral turns into your single integral from Cal 1. And so, you know, why are we doing area with a double integral? We can do area with a single integral, right? So in a way, we're not doing area with a double integral. I don't know. They kind of allude to that. That's what they call it. You know, listen, I'm going to tell you this. They're lying, okay? A double integral is volume. But let me just explain something to you. You know, a double integral is volume, and this is a height. This f of xy is a height function, z. So it's the height integrated over this area, so that it adds up to be volume. I tried to do it with that fantastic picture there. What's the height of this one? What's this height? I mean, what's sitting here is, you know, I said, oh, there's no function there, so what's there is a 1. It's z equals 1. Technically, it's z equals 1. You know what I'm doing here? I'm integrating, here's another great picture for you. I'm integrating over some region R, and my height is a height of 1. So technically, here's what I'm finding here. I am finding volume. I'm finding the volume of something with a height of 1. But listen to this. let's just say the area of this region is, let's say this area is 14. So the area of the flat floor is 14. If you want the volume, isn't it the area of the base times the height? And what's the height? 1. So what is the volume? The volume is also 14. So the area is the volume, except for the units don't jive. The area is square feet, or whatever units it is, square units, and the volume is cubic units. But numerically, the area is equivalent to the volume of something that has a height of 1. So when they call this the area of region R, I mean, they're right, but really it's the volume of something with a height of 1 over the region R. But numerically, that's the same. I'd like you to try to, right, so let's buy into the book's lie, if you don't mind. I'm joking when I say it's a lie. But let's just kind of maybe learn it like this. We should know that this is a volume, but if there's no function there, or just a 1 there, we're calling it the area of region R. When it's a function there, then it's the volume between the surface and the region R. The truth is, this is really just volume with a height of 1. But as we do the homework, we'll try to pay attention to what the book wants me to do. Sketching this region and working on this region like I did a few minutes ago, I guess I've erased it. That's kind of a big skill that you work on in 14.1. Let's try a problem here. Let's just try a quick problem here in 14.1. Yeah. Okay, here's one. I'm going to do this. Number 44. They want me to find the area using a double integral, or an iterated integral. So I'm in 14.1. It happens to be number 44. And they give me y equals x, y equals 2x, y equals 2. See what they're doing here. This is the way they word these problems. Hang on, let me read this here. 44. Find the area of the region bounded by the graph. So we use the correct language here. We're talking about a region. I want to find the area of the region. What these graphs do is they form the boundary of the region. So I want to try to sketch this region. Y equals x. Pretty famous line. Y equals x. It's supposed to be a perfect 45-degree angle there. I got a little off. Y equals 2x is a little bit steeper. It has a slope of 2. So this is y equals 2x. And then y equals 2 is, well, if that's 2 and that's 1, this is 1. Y equals 2 is a horizontal line. Y equals 2. So they gave me what they called the boundaries of the region. Now it's up to me to sketch the right region and make sure I know what I'm doing here. Excuse my language. We're going to go with this. You know, 44 actually said x equals 2. I read it wrong. So hang on, this is not 44. This is similar to 44. I made up my own problem here. Listen, with these 3 boundaries, students have a hard time. They'll shade this, or they'll shade this. They'll shade the wrong region and then go do the whole work for the wrong region. So make sure that the boundaries they give you are the boundaries of the region. So this one's easy. It's this region, of course. I mean, it's got y equals 2 boundary, y equals x boundary, and y equals 2x boundary. Nobody said this was a boundary, so don't assume it is. Nobody said this is a boundary. Please don't assume it is. So just use the boundaries that are given and there's the region. Can we set up a double integral to do this? If I'm finding area, then what goes in the integrand? Just a 1. Okay, so I'm not integrating any function, just a 1 if I'm finding area like they think I am. Remember, it's really volume of something with a higher 1. And now dy dx or dx dy. You know, there's good choices here. You know, I think I really like to kind of do dy dx is the way I like to integrate y first. But then that means I'm working top to bottom first. There's an issue here. If I try to integrate y first, I've got a lower y and an upper y. I think the lower y would be y equals x. I think the upper y would be y equals 2x. But that's only true up until this point. After that, I've got a lower y, which is the same lower y, but a new higher y, upper y, called y equals 2. So 2 different upper bounds for y would require 2 separate double integrals. Maybe I don't want to do dy dx. I could, but maybe I should do dx dy. So let's let x go first. That's dx dy means let's let x go first. So I'm going to let x go first. So x moves this way. Let's get rid of this picture. X moves this way. I'll tell you what, I think I see it very clearly. I think for x, there's a very clear curve on the left, and then x moves left to right. I think you got a clear curve on the left and a clear curve on the right. You know, when we integrate with respect to y, the bounds are y values, but they're written in terms of x. Okay? If I'm integrating with respect to x, then these bounds are x values, but they're the function written, solved for x in terms of y. So, left to right. I think the left curve is this curve called y equals 2x. But I need to solve for x in terms of y. X equals y over 2. Sorry, I flip-flopped it there. That's the name of that line on the left. That's this line with his new name. And that's the left x. So x goes from y over 2 to the right curve. What's the right curve? The right curve was this curve, y equals x. When you solve for x in terms of y, it's x equals y. Thank you. So I go from the left to the right. These are my curves solved for x in terms of y. It's just those 2 functions, but I have to solve for x in terms of y. Awesome. Now, can you tell me the bounds for y? We've taken care of x. X is moving left to right, left to right, left to right, left to right. While it does that, y, we need to let y carry it through the whole region. And so what does y do? The extreme lowest y called 0 to the extreme highest y called 2. 0 to 2. That's long and involved. That's the skills that are important for this chapter. Sketching the region, analyzing the region, setting up the bounds for a region, setting up the bounds on a double integral for integration over a certain region. And you can set it up dx dy. We could have set it up dy dx, but it would have required 2 double integrals because I had 2 top curves. So left to right worked a lot better. We don't like working in x's and y's. I mean, we don't like working, we kind of prefer dy dx, but this was better. Okay. Well, that's a nice little introduction to 14.1 and 14.2. I might do some more homework next time, but I think I'll quit right now.